So I'm very happy to introduce Jayanne English. So Jayanne's known to many of us who've been around Canada for a while. But I should just, for the younger people here who don't know her, I should say she basically originally trained as an artist and switched into science. And she's managed into her career to combine very well her scientific interests and her artistic interests, in particular being heavily involved with the Space Telescope Science Institute and things like the Hubble Heritage Project. So she is a world expert on how you make really, really cool pictures that people have for, screensavers and so on, because they're so cool looking. So today, to start off 2021, this new year, we've invited her to talk to us about how you visualize science in astronomy and in general. So Jayanne, it's all yours.
Thank you very much. Thanks for inviting me, and hello to everyone I know at UVC. What we didn't check was how this moves ahead. Okay, so what I'm going to talk to you about today is about using data visualization to explore and communicate your science. And this is under an umbrella series of talks called Cosmos and Canvas. So I'm going to provide a motivation for visualization, a motivation for using perception-based symbols. Those are ones that involve the eye-brain system. I'm going to give examples from information visualization, which is applicable to your papers, and scientific visualization, communication with the public. And then I'll just make a couple of comments about current research in visualization. So we want to do visualization because it's critically important in a number of areas. We all know that it appeals to people, inspires them to go into science, but we also want to use it. We use it because we're humans. About 70% of our brain is geared towards visualization. Visualization is important for your careers and for your things that you're trying to accomplish in science. So it's part of our cognitive tools. And of course, pencil and paper drawings were always historically integrated into science. We can just look at Galileo. But interestingly, it has quite a bit of political power too. So a lot of people feel, and it's been well described in a particular book by Tufte, that if the engineers had shown the proper kinds of visualizations to the managers, the Challenger would never have lifted off. Also, for the Hubble Space Telescope, it was supposed to not have any more servicing missions, and because of the public outcry, they were instigated again. And that public outcry is predicated on all of these beautiful Hubble Space Telescope images. So there's a bit of political power that as scientists we're probably often not aware of. Also, if you're doing something like medicine, you have these interactive tools, you move the mouse and something happens, and you're trying to make decisions if you're a surgeon during the surgery. So it can be important for making sure that there aren't any medical mishaps if you do the visualization correctly. So as well, there's humans in the loop for when you want to do quality control of your data and assessment of your big data. You really do have to have the human there. So a cognitive system includes the human. It's a combination of the human and the computer. And what I'm showing you here now is a motivation for perception-based symbols when you're doing visualization. I'm going to show you a spectrum of examples, actually just 3 examples in the spectrum. This one's in the middle. What it does is it uses graphic symbols to explain what a cognitive system is. It includes the humans that you're going to be telling your information to, the human that's running the computer and the interface between the computer. And so we can have shapes and we can have textures, and all these little things are graphic symbols that you can read to find out some information. Now let's look at the 2 ends of this spectrum. On the left-hand side, we have perception-based elements, graphic elements. We can recognize the people, we can recognize the animals. It's easy to read. It relies on human perception, which in turn is based on our physiology. It's sensory. And on the right-hand side, we have mathematical symbols. So this is culture-based. It's very powerful. but it's obscure. It requires a steep learning curve, and some people call it arbitrary. I just call it conventions, but it takes a lot of time to figure out what it's saying. So why do we emphasize this perception-based one? Well, because perception is really powerful, whether you're aware of it or not. So what I'm going to do to prove that it's powerful is I'm going to ask you all to stare at this yellow circle for 15 seconds. Then I'm going to ask you to look at the little black ring here, okay? And I'm going to ask you a question. So let's start by looking at the yellow circle, and I'll count up. Try not to blink. Try not to look at me. 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 9 3/4 thousand, 10,000, 11,000, 12,000, 13,000, 14,000, 15,000. Now look at this ring over here, and you'll see a color. What's that color? Now, if we're in a room, a bunch of you would be yelling out purple or purpley blue. Okay, so that purple is an after image, and our brain is making us see that. It requires us to see it if we stare at yellow. So we can use these after images to select pairs of colors that work with our physiology. These are called complementary colors, and we'll look at those more later. So any understanding of the information presented in a paper or in a textbook or in a newspaper or on television, this information that's presented visually is not purely intellectual. It's convolved with what is being delivered by our eye-brain system. So also I'd like you to note that nobody came up to your monitor and painted on it. It's not physical, color's not physical, but an emergent property, and it requires more than one physical input to generate some perception. Here's another illusion, if you like, that I'm going to show you. These circles are the exact same size, and one of them appears bigger or appears to jump towards you more than the other one. That's for 80% of you, 90% of you, this is going to work. And it's going to be the red one that pops forward at you or appears bigger. So artists use different words for this than scientists would. The red is warm. It's not based on temperature, but instead it's based on the fact that it jumps towards you. Blue is cool, and that goes back. Okay, so how do these illusions happen? Well, if we look at the path or physiological components involved in visualizations, we can see that our pictorial elements and our forms are detected in the eye-brain system, starting with an input that's wavelength, luminance, reflectance, texture. All of these will have an impact on what we see. It passes through a double lens right at the beginning, and it's the different focal points for red and blue that causes us to have blue to go back and red to come forward, actually. That's one of the reasons that that happens. But what happens to the image that's falling on our retina, notice that we have a non-uniform field of view. These are cones and rods. We don't have a nice grid like our CCD detectors do. These cells actually transfer the difference in luminance, not the actual absolute value, but the differences in luminance along nerves bundled into this optic nerve through a kind of a junction and then back to our primary cortex visual area. But this cortex area is not a projection screen, and a lot of the image processing happens much before anything arrives at the visual cortex. So there are different pathways, depends which cell you hit and then which nerve you go along from the lens here through to the retina, etc., all the way to the cortex. So these different pathways are called channels, and they pre-process some of the input. And what they make are called feature maps or channel maps. And there's one map for every property, such as there's a map for shape, a map for color, a map for orientation. And so the cortex receives a stack of maps and not just what we are taking from the outside of our body and projecting it onto the cortex. So here's an example. If we look at the left-hand image here, it gets divided into these 3 channel maps. So where there is red, you will have little features in the channel map for the color red. For the color black, these are the features in the channel map for the color black. Now, if we look at orientation, there's 2 lines that go like that. And in that direction also, though, we have the edges of these triangles. So a strong signal in the channel map are these that correspond with these lines here, but we also have the edges of the triangles in that channel map. So what can you do? You can use these channel maps to make more powerful image graphs. So what happens here on the worst plot here is the difference between the circle and the square. The difference in the square only happens from the circle on the very corners, on the very edges. So there's the same high spatial frequencies, so it doesn't work very well. So one of the things you can do is you can change the shape of your symbol. You've probably all learned that, but it's always best to add in a redundancy and not only change the shape, but change the color as well. This one here works really well, so you can see the difference between these different birds in this plot here. And it helps you understand things at a glance. If I had to figure out how many zeros there are in this list of numbers, I have to be very systematic, and it's very easy to miss one. But if they are colored red, it's much quicker. You can do this experiment on your friends. It's much quicker to count up how many zeros there are. So this is more at a glance. So the goals of visualization are, well, there's more than these 2 goals, but here's a couple. We want to do discovery science. We want to discover trends. And so the images we make are exploratory images, but we also want to communicate the results. So we make things that are called explanatory images. So if you want to help yourself make discoveries, then you want to produce graphs and images that help you see more quickly. In other words, at a glance, or almost at a glance. Now, some people feel uncomfortable with this. They feel like they're manipulating the data. But even when we write a paper, we have a discussion section. And in that discussion section, we give our perspective, our interpretation of our results. And the same thing happens in an image. You have to choose a perspective for communicating when you're doing this, especially when you're doing the communication of results and making explanatory images. So there is no objective image when you're communicating any more than there's total objectivity when writing a paper. So if you use it correctly, you can employ visual techniques without biasing the data or without misleading the viewer. If you don't know about visual techniques, then it's very easy to mislead the viewer, and I'll give you examples in a moment. So here's just some more examples of what you can do for your graphs and plots, and you can look this up in the Column Ware Information Visualization textbook. The strongest ones are colored red here. I think they're really very interesting. These are, again, the channels. So you have a channel for size, a pathway through your brain for size. And since color is one of the strongest feature maps, let's look at that one first. And this just mentions again that you can use redundancies. So color is one of the strongest, and we can use a very simple tool here called the color wheel, which works with visual perception. So we've already seen complements are the opposites. We stared at yellow and we got this purpley blue here. And if we stare at magenta, we'll get green and so on. And that's how you determine your complements. If you have colors that are adjacent on the color wheel, they're called analogous harmonies. And one of the things to note is that if you take complements and you add them together, if you do this in the right proportions, when you use RGB on computer monitors, you're going to get white. So you take yellow and you add it with this blue purple and you're going to get white. And if you take magenta and you add it with this yellowy green, you're going to get white, etc. You can also get a neutral gray and another in the subtractive color system. So you have something that's called, by definition, a harmonious image if the colors you employ will add to white or will add to sum up to gray, neutral gray with no color in it. It's just a definition. It's not a value judgment. Okay, so sometimes we use color tables to distinguish for one parameter different values. So for example, temperature, whether it's hot or cold, whether there's a lot of precipitation or very little precipitation. And so if we look at a grayscale, this is values. We use values for intensity. So the values go from light to dark. And if you look at the natural value order, here's an attempt to make a false color scale, which goes lightest colors at the right and then darkest colors on the left. But if you look at the rainbow color sequence, you go dark and then you go light. And if you have yellow in here, it's very light. And then you go darker and then you go lighter and then you go darker and then you go even darker. So if you have anything, and in astronomy, we have a lot of images, if you have anything that's a grayscale image to start, you're going to obliterate that when you employ the rainbow color scale. And here's an example in this graphic of precipitation in the US. It looks like half of the country has more or less precipitation than the other half of the country. But if you look at the values here, the numerical values, they are equal jumps between each of them, and there's no huge jump between this green and this green here. It's the same jump as everywhere else. So color and visualization can be misleading, and you have to be careful about that. So the numerical values below here change smoothly, but the map seems divided in half. Another tricky color map to use if you're not aware of what you're doing with it is the divergent color map. For the divergent color map, you have a breakpoint, and this breakpoint here is colored white. And on either side, you have a color that desaturates towards white. And so the distinct colors that desaturate towards white, once again, because of that going to that lightness from dark to light, you can obliterate any information in grayscale data. And also it's white, so you can't tell the difference between what's a blank part of the page and your information. So one of the solutions is to do these various things. If your grayscale values contain important information, then try using gray at that breakpoint, but make it have a similar value, that is lightness or darkness value, to the other colors. You can desaturate also to a color that is similar in value to the other colors. And you can dilute a vivid color with another color, but the whole time you have to keep your values from changing drastically. So in this example, the values are not changing very drastically, and instead of going to white, they go to this kind of cyan gray color. It gets desaturated, and you'll see how they do this a little later on. I want to point out that this is now scientific visualization, whereas we were looking at graphs before, which are information visualization. So information visualization is when you're trying to understand multidimensional data where there's relationships. And this is an example of an interactive, which you can explore with. So you're making 3D scatter plots, graphs, that sort of thing, whereas scientific visualization is like taking this map here that you have some inherent geometrical structure, and you want to visualize the image so it can be explored or inspected by eye, so you colorize the map. But the principles that I've been talking to you about, and I'm going to talk to you about, are relevant to both of these: information and scientific visualization. So I've told you how difficult it is to use a divergent color map, but you can use it when you do want to show a boundary. So what can we do here? I've mentioned that we can use gray instead of using white. So reviewing our color wheel, we have analogous harmonies, which are the sequential colors on the color wheel. We have complements, which are across from each other in the color wheel. And we have our definition of harmonious. So when you pick two colors and sum them together, you'll get either white or gray. So what I've done here is I've picked the cyan blue and put it on the left. Then I've taken a darker version of this red, put it on the right. Now I add a little bit of this red to the cyan blue, I get the color that's next to it here. If I add a little bit of the cyan blue to the red, I get the color that's next to the red here. And I keep going, and then I will get gray, if I've done this correctly, in the center, neutral gray. And if it doesn't look gray on your monitor, that's because our monitors are nonlinear. So our eyes are nonlinear and our monitors are nonlinear. So yours might not look totally neutral gray. But this gives you the idea of how you can make a compensating tones color scheme. That's what this is called when you mix to gray. So let's have an example. Let's take the Doppler shift of neutral hydrogen gas. The motion towards the viewer is blue shifted, and the motion away from the viewer is red shifted. So conventionally, we make maps in which the red shift is going away and the blue shift is coming towards us. So if you look at this galaxy with these beautiful long tidal tails, you can ask yourself which is visually coming forward, and the reds come forward visually, and the blue goes back most typically. Whereas physically, the reds are supposed to go back and the blues are supposed to come forward. So what we have been using conventionally is the map on the left-hand side here with the illusion of red coming forward. Now I don't have to lose the legend of red going away and blue coming forward if I use my compensating tones color map. The red here is going back and the blue is coming forward. And if anybody is thinking, well, that has to do with the surround color, absolutely true too. That plays a role, and you have to balance everything for that. And we are currently writing code for this. This is an early example of when I first used this kind of color scheme. And you can see this fragment of gas is flying towards us. So we are using this with the intention that this supports both the physiology will now support our intended meaning of our visualizations. And these are how we're mapping out the color schemes at the moment. And these are my collaborators. And hopefully these will be incorporated into projects that are ongoing now at ASCAP and for the Changes project, which I'll mention in a moment. Before we started, we talked about Steffi Baum and Chris O'Day, who are leading the VLA Sky Survey. And it's under the umbrella of Serata that we're trying to make advanced products. And some of the transient astronomers want to know where there's real features, real phenomena, and what the noise is. So we can use a divergent color map to point out which are real features and which are the noisy bits of the survey, especially on the quick look images before we have the first epoch altogether. So that's the example there. I work a lot in this survey called the Continuum Halos in Nearby Galaxies, an EVALA survey, Changes. And we have a catalog of 30 galaxies. And what I've done here, the 30 galaxies, each of them is observed with the VLA, and we've combined them to make this typical radio halo here that surrounds galaxies, and inserted into it a Hubble Space Telescope image that I've made of one of the galaxies in the sample. So in optical data, I'm going to explain what we do in radio data, what motivates our color scheme there. So by explaining to you that in optical data, we look at the slope of the line here when we do photometry in order to find out what the color index is. So whether a star has a larger output in the shorter, bluer wavelengths, or more, it's one like star E here. So the bluer star has the star that's bluer, that's colored red here because it's for a test for students and it's meant to trick them. This redder star is going to have a flatter slope, and the bluer star is going to have a steeper slope. So when we look in radio continuum, what we see is this kind of curve for a galaxy, but we have non-thermal radiation, that is synchrotron radiation, has a steep slope, and thermal radiation has a flat slope. And we want to distinguish regions that have a flat and a steep slope. And instead of having color indices, we call this spectral index. And that's our slope. So what we've developed here is a color scheme that's something like triple divergent color map. So in the range between what is defined usually as flat is greater than minus 0.1. So to 0.1, we've assigned a dark cyan in here. And steep is more negative than minus 0.8. We've assigned it, the complement to that dark cyan is this orange here. And in between here, we make our compensating tone map. But where it is steep, we make an analogous sequence of colors. And where it's flat, we make an analogous sequence of colors going to plum. And for steep, it goes to yellow. So that's what our color map looks like. And you can see here that we're using yellow and purple, which are complements, and cyan and orange, which are complements. So we have a harmonious color scheme. And when we apply it here to our spectral index maps, we can see that it's very flat. Right here, we've got our plum purple. And so that helps us pick out right away that there may be an AGN there. And then we can look towards the edges here and consider whether the halo has a steepening synchrotron slope out there. And we can access that more quickly than using a different color, the rainbow, for example, color map. So we are proposing to use this in other catalogs like Sarada and in visualization suites like Carta. And so we've been working up our Python examples for that. So now I'm going to give examples of scientific visualization being used for public outreach images. And the notion about public outreach images is that astronomers, professional astronomers, are asked to pique the curiosity of the public about the objects that we study. And the idea is not to present all knowledge about an object or phenomenon, but it is to build bridges between astronomers and society and get them to go and look at other sources of information once they have their interest piqued. But what's interesting for you is that these images can feed back into your professional journals. Now, because we're scientists, we really like our contour plots. So the culture of science has a very strong impact on us, but the public doesn't like it very much. They don't find these images very appealing. So what I try to encourage people to do is use techniques from visual art to create appealing versions of these objects And so this is one you can make with Spitzer, Galax, and HST data. The public desires these outreach images to be in a tradition that's been named Western image tradition of representation. And the characteristics of this is that these images are detailed, they're naturalistic, they seem to mimic nature, they're convincing, they're compelling, they seem to preserve the form of things as they occur in the world, and so we can then use them as proof. For example, in this one, we can prove that young stars are forming and ionizing gas, and the galaxies are interacting with each other. But these images that are the Western image tradition representations are constructed out of data, and that's a whole different kind of image tradition. Scientific data belong to the logic tradition of images. So these are defined as counting rather than picturing machines aggregate masses of data to make statistical arguments for the existence of a particle or effect. So if we consider our CCD data, the photons are counted by the detector. So it's a counting machine. And what we do is we take multiple data sets, which we combine together to increase the signal to noise ratio. So we're doing some statistics here. And the data sets, of course, we analyze later by using mathematics on them. But one of the best examples, I think, is a radio telescope. So this is counting rather than picturing machines aggregate masses of data. Okay, so someone else describes it. Eventually, in the logic tradition, pictures become surfaces on which quantitative information was deposited. So if we look at this image from a radio telescope, of course, we're synthesizing a mirror as the Earth rotates. So in the first hour, we have nothing because we've barely rotated. And you're going to see here artifacts from the rotation around bright sources. We're going to have circles. So as we go along with time, the image is deposited on that two-dimensional surface, and we see in the center here a supernova remnant. So going back to optical data to explain how we make color images, what we do, of course, is we just have filters which block all the wavelengths except for those we select for scientific reasons. And so we get black and white images, and we only sample little bits of the range that our eye sees. So here's the optical range, and we have a little bit here in our ionized hydrogen, and then we're using this little range here to represent our stellar light. In the shorter wavelengths, the ultraviolet, we have heated young stars, heated gas, and we have at the infrared, we have old stars. So we're doing it for the science, and it's often not in ranges visible to the eye. So to make an image, we have to decide which colors to assign to these black and white images and then combine them. So if we have a bunch of data like this, we have 6 different images. We have broadband images. So we have the ultraviolet on the left, the infrared on the right. And we go, okay, well, the ultraviolet's towards the blue end of the spectrum. We can color that blue. And the infrared is towards the red end of the spectrum, and we can color that red. But we have also narrowband filters here, and you can see the structure. I want you to note that the structure is very different in each of these. On the left, we have oxygen, we have ionized hydrogen in the middle, and we have sulfur on the right. And we don't want to lose that information. So going back to our kind of color wheel thing here, we can see what wavelengths are associated with which colors. And notice that we call this blue, but it's really purple blue, so it's a bit of a misnomer. We have yellow green and we have red orange or red. And if you look on the right, this is the theoretical color space, and you could imagine that there could be colors in all this space, but if you do tests on human beings, these are the only colors that they see out of this theoretical color space. This is a gamut of the colors that they see. And along the edge here, you can see these numbers, and those are the wavelengths associated with these colors. So again, we dealt with the complementary colors across the color wheel. Now this is how I would assign the colors for the broadband images. So there's the black and white images, and all I would do is use a program like GIMP and color one red. And I'm very careful here, so I'm not obliterating my value, my grayscale value. I'm just assigning color there. So that gives me my start on my image. But what do we do about these 3 narrowband images? Well, 502 nanometers would be up here by 500, so we could color it green if it suits us. Then these two, 656 and 673 to a human are just going to look red. Both of them are going to look red. So we don't want to color them both red. So how are we going to distinguish those elements? What are we going to use for our principles? And what I try to encourage people to do is incorporate principles from art and design to make these decisions. Now this side of the color wheel is warmer. Warm colors come forward, so you could go right from this orange down to this pink. And then cooler colors are on the other side. And so they can be these blues over here. And it depends on the relationship. So this green here is cooler than this magenta. So you can always do it relationally as well. So this is what we did, and we retained the science by doing this. We made the region right beside the star cluster green, and that way the star cluster, the green is cooler than the magenta, and the star cluster can pop forward. So if you look at this long enough, you get a bit of three-dimensionality out of it. And you'll notice that I used, our team, the Hubble Heritage team, used complementary colors, pink and green, so we have a harmonious image. So that means people will stare at it for a bit longer and have that experience. You don't need to use color. This is a really interesting one that's done by a very established artist, Alexandra Mir, who's just had very successful shows. And she wanted to know if she could access this data and make it her own. And she does not like to use color. She likes to use marks, as you can see by the piece in the background there. So she made marks for 3 filtered images, 3 different styles of marks or directions or orientations, and put them together and made this very interesting result where you can still determine or distinguish between chemicals and morphology. And it's not in the Western image tradition. But we're going to go back to the Western image tradition and look at, for example, here, radio data. And this radio data is not what your eye would see. There's nothing here that your eye sees, but it looks like it. It's very convincing. What it does is we use the colors here, red through yellow, to show the emission from supernova remnants and actually the energy. Like if it's an old one, it's going to be lower energy and it's red here. And background active galactic nuclei also have synchrotron emissions, so they have this yellow and red. These aren't stars, they're the unresolved jets of AGN. Then we have the green is thermal emission in the radio, and the blue is from the infrared. The blues are from the infrared. And where all of the colors combine, we have dusty objects. These are the little knots where stars are forming. So this is life and death in one image. And it's also been called an active galactic nuclei detector. Another example here is if we look at the galaxy on the left, especially in the past, this galaxy that has very little star formation has a large radio halo, but we expect radio halos to be dependent on star formation. So we looked at this for the Changes project, and we could probably get through what's going on by making all these contour plots, but it takes time to discern what's going on using the contour plots. So what I did was produce an explanatory image for the public where I took non-radio data and put in the disk of the galaxy, which is about 100 million light years away. And then the radio galaxy, if you just look at that, there's barely anything in the disk. And what's in the background is an AGN with jets. So that's several billion light years away, it turns out. So we called this Nature Pulls a Fast One because we were tricked into thinking that this low star formation galaxy had a huge halo, but really it was just this AGN is perpendicular to the disk of this galaxy, this background AGN. And I also am showing you here that you can make it for the public. It can go into your papers and end up on the cover of a journal. Okay, so that's the journal and the paper. Now, you have to use some tricky techniques here. For example, masking. This is an image where we have 30 galaxies and we combine their halos to make a typical radio halo. But if I was trying to put in the disk with just the algorithms available in a manipulation package, you can see you can barely see the disk there. So what we do is we create a mask. It's kind of like holding your hand up to the sun when you want to watch an airplane get close to it. We put a mask to take down the intensity in the radio data, and then we can insert in our disk of our galaxy. This is a little aside you can ask me about after, about using masking for art conservation, which turned out to be really interesting. Then we used masking for this. NASA wanted an image, but this uses radio data. I'll just let you look at that for a moment. By the way, I forgot to tell you guys to turn off the lights to look at these. So if you want to turn off the light, then you might go, ooh. So what's here is the masking together of Canadian Galactic Plane Survey data and VLA data. And this outer region here is the Canadian Galactic Plane Survey, and I masked it out and inserted the VLA data. This is a supernova remnant. When the pulsar formed, it was given a huge kick and it went zooming out from the center of the supernova remnant, and the pulsar is actually at the tip of this feature here. So we call that cannonball pulsar. So as we are coming up to using SKA precursors and mixing data together from different telescopes, we'll use this technique. And if you haven't seen it already, this is really exciting science. The image isn't finished yet. This is one that has been released. Oh, by the way, I meant to say that the previous one had over 1.5 million hits. So these can be very popular images. This one, we have to add in the Meerkat data as well. This is the ASCAP data, and these are a new kind of object that's being detected. Don't really ask me what it is because the theorists are all arguing at the moment. But it isn't a planetary nebula. It's not a supernova remnant. It's probably associated with galaxies. Now we're getting into something really complicated that we're doing. As you know, we can, with a radio telescope, look at magnetic fields. We can see the position angle, which is called the polarization angle on the plane of the sky, and that's represented by these little vectors. And then we can do Faraday rotation, which is the rotation along the line of sight of your emission. And when you do that, this image from a paper shows you if it's coming towards you, it's got all these colors for the angle of its rotation, and the grayscale is for when it's going away from you. And so for the public, we can't use contours. They won't be accepted for press releases. And so we're going to have to mask in an optical image of the galaxy with radio data. And the public doesn't understand vectors either. And it's certainly not at a glance information. So this is what we came up with for that. So we have DES data in here, or all sorts of different kinds of data actually in this one. And the filaments here give you the position angle on the sky, and the color is the Faraday rotation. So green comes forward and blue goes back. So that's what we were doing. And to make these line filaments, we use something called a line integral convolution algorithm to create those. And what it's like is you put down a random texture and then you give it your polarization angles, and it connects the vectors. It's kind of like drawing a line in sand or throwing paint in a river. I like the line and sand analogy better. It seems to fit better with what we're actually doing. So here's two more examples. These are also changes data, and one of my collaborators in changes, Jelena Stein, made the one on the bottom. It got an honorable mention in NRAO's image making contest this year, and this is the one I made of NGC 5775 using the line integral convolution method. Now, for exploratory tools, we're used to using three-dimensional cubes that are projected onto 2D on our monitor. And I just wanted to mention that we've moved into using 3D to represent 3D, and we're using virtual reality. We've done some experiments at the University of Manitoba, and what we really like is using the Vive headset. That's worked out very well, and here's an example of someone in the lab getting very excited about using the Vive headset on supernova remnant and supernova modeling data. What I like to look at are velocity fields, and this is just kind of like our tool that we had been developing. But we've taken one of our models, which has the disk in H1, so velocity data, velocity on the third axis and two spatial dimensions. We remove the disk, we make a model, then we take the disk from the model, we remove it, and we're left with the features outside of the disk, and we can study the velocities there to assess what might be happening in terms of whether it's a chimney blowout or material flowing in like high velocity clouds. And I took this to the IdeaViz lab at the University of Cape Town. Very exciting. There's a new paper that will come out very shortly on that, let's say in the next couple of months. And here we're using a control device to move our data around, and you can see we can get our coordinates and so on. Okay, so here's a summary of what I've talked about during this colloquium. If you want to have more information about some of the techniques, then I have a paper. It's on the AstroPH, a beta version's on the AstroPH archive. So you can get it for free. I started off with the motivation for visualization. It's an important component of a cognitive system, especially those that include computers these days. And I provided motivation for perception-based symbols, and those are ones that use the eye-brain system. And the illusions showed the impact of perception. And so if we understand our perception, we can make clearer graphs, we can make clearer maps by using what we know about our physiology. We make it easier for people to read if we work with our physiology as well. For information visualization, you can use channel maps in the eye-brain system to help you create something that is more at a glance when you're trying to communicate. In scientific visualization, I showed some different color maps that you can use to aid you in your discovery science. And in particular, I focused on communication with the public, all the techniques we use that are computer technical, almost photography techniques, as well as techniques from art and design, which help the public read your image. So the images I divided into exploratory and explanatory, but actually the image you make is going to end up being both and can lead back to discovery science, inform your observing proposals, and be used in your journal publications. So there I am. I hope I haven't run too far over time, Doug.
Oh, that was good.
Okay.
Thanks very much, Jayanne.
Welcome.